Good morning, good evening, and good night, depending on the time when we are going to watch this lecture. Welcome to this lecture. In this lecture, we are going to discuss again a very important topic on the state of matter chapter. That is, we are going to discuss the liquefaction of the gases. This is KK Mukherjee in the Science with Mukherjee Sir YouTube channel. In this lecture, as we have already decided, that we will discuss on how we can able to liquefy a gas. They are basically a particular conditions, particular pressure, particular temperature, and how do we able to assess, how do we able to predict all those conditions, and we will discuss in this lecture, and we will learn how we can able to predict this specific condition for a gas, particular gas, because it will be different for different gases, and the isotherm of the gases will be helpful to understand this condition, to predict these conditions. So what is isotherm? That we already understand. In our lecture number 2, we have already discussed about the Boyle's law when we are plotting the pressure volume relationship, the graph of the pressure volume, and when we keep the temperature constant. This is called the isotherm of the gases. It was Thomas Andrew was the first person to obtain the detailed data on the pressure, volume and temperature relationship of the substance in the gaseous and liquid phases. He plotted the isotherms of different temperature, and he able to predict and come to a conclusion regarding the particular temperature and particular pressure and particular volume at the time the gas is would be going to liquefy. And he has used the isotherm of the carbon dioxide gas. Let us first understand this graph. In this graph, we will plot the pressure and the volume, and we will plot the different isotherms. The isotherms, that is, we plot the isotherms at the 50 degrees Celsius. This is the isotherm at 50 degrees Celsius. Then we plot the isotherm at 31 degrees Celsius. You can observe the three isotherms, that is at 50 degrees Celsius and 31 degrees Celsius and 30.98 degrees Celsius. You can easily observe when the gas, when the isotherms at the higher temperature, at that time this gas behave ideally, that its curve is almost identical to the ideal curve. But as we go on decreasing the temperature, the shape of the curve, you can see that is been changing, that is been significantly changing. And at the temperature, when the gas is at the 50 degrees Celsius, at the temperature he could not able to liquefy the gas. In spite of applying lot of pressure, with a lot of compression on the gas, but he could not able to liquefy a gas. But when when the gas temperature of the gas has been reduced to 30.98 degrees Celsius, at that time what you observe, and it is when the pressure is 76, when the pressure is 76 millimeter of Hg, at that time what he observed, that there is the first appearance of the liquid carbon dioxide is observed, that you can see here. And at that time the shape of the curve is totally different from the other isotherms. And in these isotherms, this temperature at which the gas has been liquefied, it is called the critical temperature. So we can write the critical temperature and it is denoted by Tc. Critical temperature is denoted by Tc, and it is the, you can write the definition of the critical temperature. It is highest temperature at which gas is liquefied, and this is called the critical temperature. And at this temperature, the temperature is here is 30.98 degrees Celsius. That is for the carbon dioxide gas. Similarly, for the other gases, you will find the critical temperature is different, that we will discuss for different gases. So what you observe, when the isotherm on the higher temperature, it is not possible to compress, it is not possible to liquefy the gas by compressing, because at that time what we will apply, pressure we will apply, that will be not sufficient to convert the gas into liquid. But when it is 30.98 degrees Celsius and when the gas has been up to the 76 millimeter, the CO2 was the gas. But after this 76 millimeter, what he found that there is a liquefaction of the gas. The first carbon dioxide liquid he observed in this appear for the first time, and this temperature is called the critical temperature, highest temperature at which you can able to liquefy the gas into the liquid. So there is a condensation start from this pressure, and this pressure is also called the critical pressure, and the volume, 1 mole of volume at this temperature is called the critical volume. So these are basically critical constant. So Vc is denoted by critical volume, and Pc is denoted by critical pressure. So all these are called the critical constant. This is called the critical constant. So we understand the critical constant, that is includes this critical temperature, critical volume and the critical pressure. And for every gas, this is a unique one. For carbon dioxide, what we have observed, that is 30.98. for hydrogen, for helium, for any type of gas, you will find the critical temperature is different. At a particular temperature, this gas will be liquefied. Now we take the isotherms of the below the 30.98 degrees Celsius. What will be the shape of the isotherm? Here you can understand at 30.98, when the pressure is increases to 76 millimeter and upwards, when we increase the pressure further, we can see there is a steep rise in the pressure. Pressure has been increased like anything that you can see from a very minimum change in the volume. You have to increase this pressure to a very significantly. That steep rise, the gradient of this curve you can find that is very steep. And what it shows? This shows now we are compressing the liquid. Here, this isotherm we will call, that is the isotherm for the liquid only, because at this stage, up to this stage, it was a gas, but after this, it was no longer gas, it is a liquid one. So we are compressing the liquid. Naturally, you cannot able to compress it much more easily. There is a very much difficulty because there is a repulsive force between the molecules that you can see, and they will always resist the compression, and that will, you can find the curve is very much steep. Now we will take the isotherms for the another, that is the isotherm we are taking for the 21.5 degrees Celsius. At this time you can see this isotherm up to this point. This is a gas up to this point, but when it reaches this point, you can see further compression on these gases. It will not going to increase this pressure. That you can see the pressure is become constant one. Pressure is become constant one, and at that time you can find the horizontal line. What it means? This means that when you are compressing, means we are adding this pressure, and this pressure is utilized to condense the gas into the liquid. So at that time, what you will find? You will find in this state both the gaseous state, also in the liquid state. So you can say this is the point, there is a coexistence of gas and liquid. But after this point, when it's reached, means all the gases has been condensed into liquid, and after that you will find there is a very steep gap. So here you can see one thing, that this is the suppose volume V1, and at that and when it reach this stage, you can see this will be volume V2. Suppose from this V1 to V2, when it is increased the volume, how much pressure you have been increased? You can see this is P1 suppose, and this is P2. There's a lot of pressure has been increased. Basically, we are pressing the liquid air. This is at this point, this is all gas, and here that is 100% gas. After that, when it enters this dome, it will be a coexistence of the gas and liquid. But after that, this will be the isotherm of the liquid. Again, you can see another curve. This is this curve, where you can see 31.5 degrees Celsius, where also you will also observe this type of things. So what is there? Below the critical temperature, the curve has a different nature, totally different nature, but all the curves is identical, you can see, but difference is on the horizontal point. The horizontal line will be different as it is going to, we are decreasing temperature, the horizontal line goes on decreasing and increasing, that you can able to see. But here in the critical point, this is like a point. So if we join this, you can find a dome. You can find a dome here, right? And in this dome is created. Here you can see there is a existence of the two phases, that is liquid phase and the gaseous phase. Okay, so we can understand how the gas has been liquefied. Gas is liquefied. It will not be liquefied as above this critical temperature. Gas will only be liquefied at this critical temperature or below this critical temperature, but above this you cannot able to liquefy the gas. Why? It is already discussed in your lecture number 1. You can remember that it is basically the balancing of the thermal energy and the intermolecular interaction energy, attraction. The molecule, the air, you can see when the gas will going to liquefy. Gas will be liquefied at that point when the thermal energy will be minimum, and at the same time the intermolecular force of attraction will be maximum. And at this temperature, at this critical temperature, what is going to happen? The thermal energy of the gas is very less, and that is why when we are compressing it, the molecules are touching with each other, and there is the creation of the high intermolecular force of attraction that you can see here. So when previously when the volume was high, this will be like this. When the volume is low, what will going to happen? The distance between the molecules will be very, very less, and it will going to, the phase of the state of the matter has been changes from the gas to liquid. So you understand how the liquefaction of gases is being done, and it is basically a process. In this process, what we find, the thermal energy of the gas molecule will be a minimum point, will comes to the minimum point at that time when we make these molecules much more closer. So intermolecular force of attraction going to be operated, and at that time gas will be liquefied into the liquids. Gas will be condensed in the liquid. So you understand, and this type of behavior you can observe for all the real gases. For all the real gases, but the temperature will be different. Now we are going to discuss how this critical temperature is being correlated with the van der Waals force of van der Waals constant. We know already in van der Waals equation there is a two constant, constant A and constant B. Constant A is basically correlates with the attractive forces. That we are going to understand now. Now we are going to discuss how critical temperature is going to be influences by the intermolecular force of attraction. That you can easily understand that if the intermolecular force of attraction is higher, then critical temperature of the gas will be higher, and higher the intermolecular force of attraction, then the gas can be easily liquefied. And this internal force of attraction that will be correlates with the van der Waals force of attraction, van der Waals constant, that is A. So where A is higher, means critical temperature of the gas will be higher, and that we are going to discuss with some example. Now we can easily observe from this data that there is a different gases I have plotted, and it is in the increasing order of the transition temperature. Increasing order of transition temperature. You can see helium gas have the lowest transition temperature, that is 5.2 Kelvin, followed by hydrogen, followed by nitrogen, oxygen, carbon dioxide, HCl, NH3, SO2. And exam, this type of question you may face, that you have been given some set of gases and you have to arrange in order of increasing their transition temperature, or we can say in order of increasing their van der Waals constant. So you have to remember it. One thing we can observe, that the van der Waals constant is directly correlated with the transition temperature. As the van der Waals constant is increasing, you can see helium have the lowest van der Waals constant, that is 0.034, whereas its transition temperature is the lowest. So van der Waals constant is lowest and transition temperature is lowest. Hydrogen also you can see it is followed by the helium, 0.244 is van der Waals constant, and its transition temperature you can see 33.2. Whereas in nitrogen you can see this, and in the SO2 you will see the van der Waals constant is 6.7, whereas its transition temperature is 430. So as the van der Waals coefficient increasing, the transition temperature also increasing. So higher the intermolecular force of attraction, higher it will be easier for us to liquefy the gas. So if the transition temperature is higher, means gas can be easily liquefied at the room condition, at the room temperature. But for this gas, that is helium and hydrogen, that the gas will be called as a permanent gas. Sometimes question has asked why it is a permanent gas. Because to liquefy the gas, you have to be cooled down. It has been cooled down by, you can see how much, 5.2 Kelvin, means you have to go to the minus level. You have to go the minus of temperature, that is, in that case you will be able to liquefy it, right? So this gas cannot be liquefied very easily until and unless you have bring down the temperature to a bare minimum level. At that time it will going to be liquefied. What will going to happen? At that time the thermal energy of the molecule will be reduced significantly and the velocity of these molecules will be reduced. So it can be, when you are compressing it, though it will be liquefied, and the force of attraction will be at the time the appropriate for this liquefaction process. So you can understand the how the van der Waals forces going to influence, van der Waals constant is going to influences the liquefaction of the gas, and the critical temperature is dependent on the intermolecular force of attraction. Higher the force of attraction, higher will be the critical temperature and higher the chances of the liquefaction of the gas, that we can able to liquefy the gas very easily. Now we have some relationship that is also be helpful. What is the relationship? And this relationship is basically with the critical constant. We know what are the critical constant, that is the volume, temperature and the pressure. For the volume, if we see, Vc is the critical volume. How it correlates with the van der Waals constant? It will be 3b. Pc is the critical pressure. It will be correlate with A by 27 B square. We know these are two, are A and B are the van der Waals constant. And for the Tc, you can see that will be 8A by 27 R into B. This is a very, very important relationship. And now what is the relationship between the pressure, volume, temperature at the critical points? This relationship you can see it is like this. CVC is equal to 3 bar I R into DC. So we can see from this, we can able to see compressibility factor for this critical point. It will be, you can see, 3 by 8. Now on another temperature that we have learned in the previous lecture, that is the boils temperature. How the boils temperature correlated with this critical temperature, which is higher. Boil temperature, if we correlate with the van der Waals constant, it will be given by A by RB. Where critical temperature, you can see it is given by 8A by 27B, 27RB. So from this, you can easily able to say the boil temperature is higher than the critical temperature. So these are very useful information that will help you to understand the process how the gas is going to be liquefied. Gas will going to be liquefied at the temperature, at the specific temperature and pressure that is being we have discussed here, and that is the critical constant, we will say. And gas cannot be liquefied until and unless we reach that temperature, and after that gas can be easily liquefied. And this liquefaction, there is a different processes of the liquefations that we will discuss in the next lecture in the Joule-Thomson coefficient, and that is also very important effect that we are going to discuss in the next lecture. Hope you understand all the points. If you are watching this, thank you for watching this lecture, and thank you.